Chapter 3.7, Optimization Problems, Day 3. Now remember, optimization is finding the maximum or minimum of a situation. A few steps. 1. Variables. Assign them to all your quantities. If possible, make a sketch. 2. Write a primary equation. This is what's going to be optimized. What do you find the max or minimum of? Example, profit, cost, area, volume. Usually there'll be more than one variable. To deal with that, write a secondary equation. All right? And then substitute that in to get rid of those extra variables. Once you've done that, decide on a domain. What makes sense in a situation. There's no way a business can have negative costs, so you always cut those off at 0. And once you've got all that done, do the actual optimization, which involves the first derivative test. So let's do a problem. All right, so a rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches each. And the margins on the left and right are to be 1 inch each. What should the dimensions of the page be so that the least amount of paper is used? This question is just crying out, draw me, draw me, draw me. And you can see in the original book, it actually drew it out for you. Decided you guys have the ability to draw a picture every once in a while. So let's draw this out. We have a rectangular piece of paper with some writing in it. And the margins from the edge of the paper for top and bottom are to be 1.5 inches. So this gap here is to be 1.5 inches, and this gap here is to be 1.5 inches. Left and right is to be 1 inch. And from there, we have our drawing. We got our variables need to be assigned. I'm going to call this width. And just for some odd reason, I'm going to call that height. H and W are going to be my variables. So my primary equation is going to be the dimensions of the paper. All right, so the dimensions of the paper, area will be H plus 3 and W plus 2. Let's FOIL that, makes it a little easier. So we got first would be HW plus 3W plus 2H plus 6. Now our secondary equation is going to involve the area of the print, the printed area. And we know that the printed area is 24 square inches. And that's going to be H times W equals 24. And I need to solve for one of those variables to put into that first equation. So I'm going to divide by H, W equals 24, divided by H. Every place I see W, I will substitute. So area equals H times 24 over H, plus 3 times 24 over H, plus 2H, plus 6. Clean this up a little bit. A area equals 24 plus 3 times 24 is 72 over H plus 2H plus 6. And now I can derive it. I'm going to go to a clean page to derive it. Copy that there. Clean page. Paste. Now, take the derivative. A prime equals 24 derivative is 0. 72 over H, that's 72H to the negative 1, so it'll be negative 72H to the negative 2, plus 2 plus 6, which derives down to 0. All right, so find our critical numbers. Let's get this into fraction form. So this is negative 72 over H squared plus 2 Forgot to decide the domain. Again, we're talking area, so it needs to be larger than 0. It can't be any too big, so it'd probably be less than 24 because that was the area of the printed area anyway. So we'll set this equal to 0. I'm going to get a common denominator. So a prime is 2h squared minus 72 over h squared. And set that equal to 0 and find our critical numbers. 1 at the bottom is 0 and h is 0. The top is 0 when h is 6 or negative 6, but negative 6 is not in our domain, so we just need to check 0 and 6. So here's 0. Here's 6, and kind of throw an n there at 24. So check between 0 and 6. Check 2. 2 times h squared. 2 times 2 squared is 2 times 4 is 8. 8 minus 72 is negative. Negative over, that'd be positive, is negative. Check something larger than 6. We'll check 10. 2 times 10 squared is 200 minus 72 is positive. Over positive is positive. So we can see we have negative to positive. We have a relative min at 6. So the minimum value is at 6 when h is 6. If we go back to the question, when h is 6, a minimum happens. That means W is 4, but we're looking for the dimensions of the paper. So if we look at the paper, it needs to be h plus 3, which is 9, by W plus 2, which is 6. So the least amount of paper they can use is 9 by 6, which will give you 72 square inches, or sorry, 54 square inches of paper. Let's try and squeeze one more problem in here. A rancher has 200 feet of fencing to enclose 2 rectangular corrals. What dimensions should be used so that the enclosed area will be maximum? Right, so first off, here's our picture, and we want area. Well, area equals 2x times y. There's our primary equation. Our secondary equation is all these fences right here need to add up to 200. So I see 4 x's, I see 3 y's, that needs to equal 200. All right, solve for either x or y. From the looks of it, it's going to be easier to solve for y. We'll get fewer fractions. So we got 3y equals negative 4x plus 200. I'm sorry, it'd be easier to solve for x. Doesn't matter. Divide by 3, y equals negative 4 thirds x plus 200 thirds. And we'll substitute that in. Area equals 2x times negative 4 thirds x plus 200 thirds. I'm going to do a little distribution. A equals negative 8 thirds x squared plus 400 thirds x. Go into a new page. And we'll derive it. A prime equals 2 times negative 8 thirds is negative 16 thirds x plus 400 thirds. We need to decide where is that equal to 0. So 16 thirds x equals 400 thirds. I'm going to set it equal to 0 and add 16 thirds to both sides. We can cancel the 3's because both of them have 3. We can divide by 16. X equals 400 divided by 16. X equals 25. Do a sign chart. No, it's fencing, so it can't be less than 0. Can't be more than 200. So if we check between 0 and 25, we get 1. Be positive. If we check between 25 and 200, we can check 100. Negative 1600 plus 400 is negative. So we got a relative max at x equals 25. We go back to our question. What dimension should be used? Well, x should be 25. That takes up 100. The remaining 3 pieces should be 33 1/3. That will give you a maximum area for your corral. So in conclusion, when optimizing, 1, assign variables. Draw a picture. 2, write a primary equation for the situation to be optimized. It may have more than one variable in it. If it does, write a secondary equation to eliminate those extra variables. Decide on a domain that makes sense for the problem, and then use the second derivative test to optimize the situation.